In this video, we will learn about Newton's method. We know that polynomial functions often have roots where they meet the x-axis. As shown in this animation, Newton's method gives us a way to gradually approach a root step by step. The mathematical details behind this process will be the focus of this video. After that, we will see how different initial guesses affect which root we eventually converge to, a sneak peek of which is shown here. We will then explore what happens when the curve has repeated roots. Finally, we will consider cases where the polynomial doesn't have enough real roots. In that situation, some of its roots must be complex. We will end in the complex plane, where we will explore a visually appealing and mysterious phenomenon that appears when Newton's method is used to find complex roots of polynomials. Let's start with a simple quadratic function. We can find its roots using the familiar quadratic formula, which I'm sure you've learned before. When we plug in the coefficients of the three possible terms, we find that the roots are at -1 and 1. So let's mark those. And yes, just by looking at the curve, it was already obvious that the roots were here. But keep in mind that I sketched this curve for educational purposes. But in reality, we would not know yet what the curve looks like. For all we know, it could have looked like any of these different possibilities, with different roots. It might have one root, or maybe even no real roots. So my point is that in the real world, we cannot know in advance that a curve looks exactly like this. Now let's move on to a cubic function. To find the roots, we set it equal to 0. If we assign p and q to the different coefficients, we see that p equals -1 and q equals nothing. It equals 0. There is a formula called Cardano's formula that you have probably not heard of. It's so large that it cannot even fit in a single line. Looking at this complicated formula, we can already feel why it would be nice to have a simpler method for finding roots. But if we do use this formula, we can obtain the values of all three of the roots. Now let's move on to a quartic function. Here, we need to assign different letters to the different coefficients. But in this case, the formula for finding the roots looks like a real nightmare. And hold on, the nightmare does not end here, because there's more. And you think we're done now? Nope. So even though a formula does exist, I don't think we would want to go through this nightmare every time we want to find some roots. For instance, if we flip the curve in this manner, every single one of the equations would have to be computed again. Now let's move on to a quintic function. I know the previous formulas looked pretty scary, but for a quintic function, an old paper from 1824 actually proved something even more surprising. Not only is there no general formula for such equations, but it's theoretically impossible to create one. So perhaps we could instead factorize the polynomial, which should always be possible. And if we factorize it, we can definitely obtain all the roots. However, coming up with the factorized form has no easy method other than trial and error, which could take forever. So we need a better method, a method that works for any polynomial. We will use a simpler cubic example to demonstrate Newton's method first. This equation has 3 roots, shown by the crosses. Let's first focus on a smaller segment of the curve. Of course, at this point, we don't know the exact intersections yet. Let's start with a random guess of 2.80. This is quite far off, and it's clearly not the correct route. Now, let's find the point on the blue curve whose x-coordinate is 2.8. At this point, we draw the tangent line to the curve. This tangent line intersects the x-axis at the green cross. We want to find the x-coordinate of this green point because it's closer to the actual root of the blue curve than the orange cross was. To do this, we first differentiate the blue function. This lets us find the slope at x of 2.8. Then we substitute the slope and the coordinates of the red point to find the equation of the tangent line. The green point is where the tangent line equals 0. This happens at approximately x of 2.1. So now we know the new x-coordinate, but doing this step by step is a long process. So next, we will derive a compact formula that we can use directly, almost blindly. Let's say the horizontal difference between the two crosses is delta x. The length of the dashed vertical line is delta y. The slope of the tangent line is given by the ratio of these two quantities. And at this red point, this slope is the derivative evaluated at x0. Here, delta y is simply the value of the function at x0, and delta x is the difference between the two x values. Now let's rearrange this equation by moving these two terms around. Then when we isolated x1 on the left-hand side. And now we have an expression for x1 that depends only on x0. In the same way, x2 depends on x1. Then x3 depends on x2. And this continues for as many steps as we want. This gives us the general formula for Newton's method, which can be used directly to find the next value of x whenever we know the current value. Now that we know that x1 is 2.115, we should move the red point, the tangent line, and pretty much everything else to this new point. Let's also rearrange our equations so that they're organized more clearly. To find x2, we can now simply use the formula. We substitute the expression for the function, as well as the expression for its derivative. Since we already know that x1 is 2.115, we plug this value into every occurrence of x1. Evaluating all of this gives us x2 of 1.768. Let's mark this point on the graph. Then we move all of our visual elements to this new point. The purple cross already looks pretty close to the actual root. Once we zoom in, we can see that we are still not quite close enough to the root. To make the next few iterations easier, let's substitute the full expressions into the black formula. To find x3, we only need the value of x2, which we already have. Using the formula, we can calculate x3. Let's mark that on the graph as well. And once again, we move everything to this new point. It looks like we're almost at the root, but we should not stop just yet. So next, we need to find x4 using x3, which gives us x4 of 1.642. Let's mark this point on the graph. Notice that it almost coincides with the previous point. However, we still shouldn't stop, because x3 and x4 are not exactly the same. So let's find x5 using x4. We find that x5 is exactly the same as x4, at least when both values are rounded to 3 decimal places. In reality, they're still not exactly the same if we use higher precision. But at this point, the difference is between x4 and x5 is so small that we can safely stop. Now let's return to the big picture. Recall that this function has two other roots, but our method did not find those roots. Why not? Can we find those roots at all? Or are they impossible to reach? We'll find that out later. Next, we will use a different starting value, negative 2.8. This point lies on the far left side of the graph, as shown by the orange cross. As before, x1, the next point, is where the tangent line intersects the x-axis. So we use our formula again and plug in x0 to get the value of x1. Then we plug in x1 to get x2. After that, we plug in x2 to get x3. As I mentioned earlier, we can use this formula almost blindly. Keep plugging each new value back into the formula until two consecutive values match, at least to 3 decimal places. And it looks like x4 and x5 do match. Now that we have the numerical values, let's run the graph visualization for each subsequent iteration so we can see exactly what is happening. At each step, we draw a cross at the x value we have found. Then the tangent line intersects the x-axis at this new point. And when we zoom out, we can see that we have converged to the root on the left-hand side. This is different from the root that we found earlier, because this time we used a different initial value. So let's talk about that. The function has 3 roots, and depending on where we choose the initial point, Newton's method can converge to a different one. Let's play a small game. For each new starting point, try to guess which root it's gonna converge to. Okay, to be honest, I did not design this game very well, because the colors of the points seem to give away the answer from the beginning. But the answer is not necessarily just about which root is closest. It also depends heavily on the slope at the initial point. That slope determines where the tangent line takes us next, and the next point then determines the rest of the journey. The different colors appear to be separated at the 2 stationary points. Depending on which side of the stationary point we start from, we converge to that particular root. Now let's learn something about the formula itself. This is called the Newton Raphson Method. As the name suggests, this method is connected to both Isaac Newton and Joseph Raphson. Newton developed an earlier version of the idea while working on equations using successive approximations. Later, Raphson presented a clearer and more direct version for polynomial equations. Let's analyze the step size, which is the fractional part of the Newton Raphson formula. At x of 2.80, we compute the step size like this, and it turns out to be 0.68. Let's draw the relevant elements at x of 2.8. In particular, this shows that the orange slope is the slope of the tangent line, while the length of the dashed line represents the value of the function. As the iterations continue and we get closer to the root, the step size becomes smaller. Intuitively, this makes sense. When we're far from the root, the y value is still large. So we take a larger step because there is still a long way to go. But when we're close to the root, the steps become smaller because we're almost there and we wanna converge gently instead of overshooting. Now, when we shift the blue curve upwards, the roots change and eventually two of them coalesce. If we move the curve even higher, those two roots disappear, leaving us with just one real root. Now let's say we start at x of 2.8, just like we did before. We will now perform the iterations one at a time using the formula. Keep in mind that there is only one root now, so that is the root that we are trying to reach. At first, it looks like we're getting closer and closer, just as we expected. Oh dear, now it seems that we're heading in the wrong direction. Thankfully we're back on track, and it looks like we're moving leftward again. Uh-oh. Once again, we get sent back to the right. We just cannot seem to get past the minimum point. Still, we have to keep trying, because there's nothing else that we can do. This time, we seem to be gently wiggling around the minimum point. But now it looks like we're stuck here. Will we ever reach the red root if we keep swinging around this minimum point? I don't know, let's find out. Whoa! Suddenly we flew to the other side of the red root, and now we seem to be converging toward it nicely. Finally, we have converged, even though it took us more than 25 iterations. The reason we struggled this time was because of the minimum point. When we start from values near it, we tend to get pulled toward that point, which makes us look stuck. However, there is a maximum point as well. If we start from values to the left of this maximum, then we converge smoothly to the root without running into the same difficulty. Keep in mind that no matter what starting value we choose, we always converge to the same root in this case, which is the red one. Duh. Now let's lower the curve. When it just touches the x-axis, there is a green root, which we reach from the green regions. But recall that there is also an orange root here, because we have repeated roots at this point. When we lower the curve further, there are 3 unique roots again. Depending on where we start our journey, we can reach different roots, as indicated by the 3 different colors. However, when we raise the curve, these unique real roots and their corresponding colors disappear. But we know that a cubic function must have 3 roots, right? So where did the other roots go? Well, the 2 remaining roots can be found in the complex plane, which is visualized here. We can also apply Newton's method in the complex plane as shown in this animation. However, this process is not exactly the same. This leads us to a visually beautiful and mysterious phenomenon in mathematics which is called Newton's fractal. We will explore Newton's method in the complex plane in more detail in a later video of this series, so stay tuned for that. Before we move on to the next video, if you enjoyed this video and found it useful, please consider liking, commenting, and subscribing to support the channel, so that I can continue making videos like this in the future. In the next video in this series, we will learn more about Newton's method. For example, so far, we have only covered polynomial function. We still need to discuss other types of functions, as well as other applications of this method. That will be the focus of the next video, which should be on your screen right now. So be sure to watch that next.